All right, are we ready?
Check, check. You hear me
All right,
well?
our next speaker is Eduardo Lanari, and he will speak about fibrations and lax limits of infinity 2 categories. Please go ahead.
Thank you all for being here, and thanks to the organizer for giving me the opportunity to speak at this year's CT. The goal of the talk today is to talk a little bit about recent developments on the theory of infinity 2 categories that my collaborators and I have produced in the past year, I would say. There's some more recent stuff that just came out, but this is sort of one step back with respect to that. And the main topics will be that of fibrations or certain classes of fibrations. And I will explain in a second which one and what the motivation is and what we want to achieve. And then also talk a little bit about lax limits, some interesting results in that respect. And also, although it's not in the title, I will also talk a little bit about co-finality in this context. So the environment is that of infinity 2 categories. So let's start, and I'll give you some motivation, and I'll try to make it as self-contained as possible for those of you that are not necessarily too familiar with the infinity categorical word. So keep in mind this proportion here. So basically, we think of the role that infinity 2 categories play with respect to infinity categories or infinity 1 categories to be the same as, or roughly the same, I would say, a homotopical enhancement of what happens in the ordinary case. So 2 categories are an environment where 1 category can be framed, developed, and also it allows us to even just state sometimes universal properties. And every time there's some construction which is 2-dimensional in nature, that's the thing we need to move to. So in some sense, we think of infinity 2 categories as a necessary piece to study infinity 1 categories, but also interesting in themselves, just like 2 categories are for ordinary category theorists. So all of what I'm going to talk about is part of an ongoing collaboration with my colleagues Andrea Gagni and Jonathan Arpas, and we've developed some technology for infinity 2 categories, some examples of which are weight tensor products, fibration, and Oplax weighted colimits, all of which will be hopefully mentioned during this talk. Okay, so brief recap on infinity categories, just to make sure we're all on the same page here. We use marked simplicial sets to model infinity categories. These are simplicial sets endowed with distinguished subsets of 1 simplices that must contain the degenerate ones. So we think of marked 1 simplices as being some sort of invertible simplices or equivalencies. Therefore, we require them to contain the identities, so the degenerate 1 simplices. A simplicial set is oh, by the way, they're not necessarily going to be marked. Like there's a way of modeling infinity categories with marked simplicial sets, but you can also use just bare simplicial sets. So the definition of an infinity category that we're going to use is that of a quasi-category, which is also called a weak Kang complex. So it's a simplicial set that has the right lifting property with respect to inclusions of this form. This is the n simplex, and this is the n simplex minus, if you want, the interior and the face opposite the vertex I. This is just a geometric interpretation of that. And this allows you to recover all the composition and higher coherencies that you need, that you would like to see in an infinity 1 category. So what's the reason for the name infinity 1 categories or infinity 2 and so on? This is often roughly summarized by saying that you have sets in every dimension up to infinity, and above dimension 1, in this case, everything is invertible. So one way of encoding this that can be made actually very precise is to think of them as being enriched over infinity 0. Basically, you go 1 step down, and infinity 0 categories are infinity groupoids or spaces. So infinity 1 categories are categories weakly enriched over spaces or homotopy types. And in fact, we can construct a space of maps between any given pair of points. So this somehow illustrates how, I mean, part of the enrichment, if you want, just exhibits part of that. So whatever model for infinity 2 categories you want to use, it ought to be enriched over infinity one categories in some sense, or at least you should be able to exhibit an infinity one category of morphisms given 2 points, to say the least. Okay, so for us, infinity two categories will be encoded by scaled simplicial sets. These are simplicial sets which are equipped with, similarly to what I said a couple of slides ago, a subset of the two simplices containing the degenerate ones. You can also have models where you also mark the one simplices, but that can be recovered simply by having just the two simplices, which are thin. And in fact, this can be proven for every n. You can just have the last one, and then all the others can be recovered sort of inductively. So it's pretty simple. As a let's say the underlying category is very simple to understand, very easy to understand. And following the paper by Lanari on the good Willy calculus, where he introduces infinity by categories, we will use these scaled simplicial sets, and we think of the thin two simplices as being somehow the invertible two cells. These are the ones that we need to be able to say when something is a composite of something else, when one cells are composite of other one cells. Otherwise, we wouldn't be able to distinguish that. So it's a theorem that has sort of two contributions. One is by Lanari, where he builds a model structure which has fibron objects which he calls infinity bicategories, and then he has something else which he calls weak infinity bicategories, which is much easier to define. And my collaborators and I prove that the two things agree. So putting together these two results, you get a model structure on scaled simplicial sets, which has a pretty simple description, just like the Royal model structure on simplicial sets say. The fibron objects are the infinity bicategories, which are detected by right lifting property against quite a simple set of anodyne maps. So it's pretty easy to understand. And this gives you a model for the homotopy theory of infinity two categories. But because it is Cartesian closed, it is in fact an infinity three category, an infinity three ambient category for infinity two categories. So what's the motivation behind fibrations? Classically, op fibrations have been used to encode functors of this form. You have an op if you want op fibrations and so on. Because for ordinary categories, it's not too hard usually to define functors of this form by hands. Maybe they're not too popular in ordinary category theory, but when you move to the homotopical realm, then like homotopical in mathematics, they are pretty much ubiquitous. That's the most prevalent way of building functors into cut infinity is to define them via fibrations. So we would like to do something similar for infinity bicategories. So have fibrations that model functors into something that we will see what that is. In the ordinary one case, also even just infinity one case, we have two possible variances. We can either have, let's say, covariant or contravariant functors. When we move to dimension 2, now we have 4 possible dualities. So there will be 4 kinds of fibrations to encode this. And because of the lack in symmetry of the simplicial shapes, this cannot be recovered simply by taking ops. And there's not really a co-operation in simplicial sets. So we have basically 2 classes which both have 2 subfamilies, let's say. So 4 variances in total. And this is just what I just said. So these 4 kinds are basically subdivided into inner and outer, and then they both have co-Cartesian and Cartesian. And the correspondence is as follows. So inner co-Cartesian is the simpler one. So it's B into cat infinity. Now here B is an infinity 2 category, and cat infinity is the infinity 2 category of infinity categories. Basically, this is the homotopical counterpart of the 2 category of categories. And then if you remove the co, this would be B op co into cat infinity. There's a trick for remembering that, and if you're interested, I'll tell you later what corresponds to what. But basically, you see there's just 4 possibilities. Okay. So this is just a sort of brief overview of what these things would like what we would like these things to model, let's say. So the definition, which I won't give into details, I don't want to list all the lifting properties that these maps need to have, but just bear in mind that there are some point set properties, so some technical requirements, just like when you require a Cartesian fibration of infinity categories to be an inner fibration, let's say that's sort of a point set theoretic requirement. And then the sort of model independent one, the interesting thing is that we require a sufficient supply of co-Cartesian or Cartesian edges, depending on what we're considering. And these are defined, to define them in general, you need to work a little harder, but in the fibrant case, this can be defined as the edges F, such that this square is a pullback in the infinity categorical sense in the category of Marx simplicial sets, or a pullback of infinity categories, basically. So the definition is formally the same, and of course this is the same even for infinity M categories. It's just that if you want to define it via lifting properties, you have to work a little harder than that. And luckily, we were able to prove, based on a previous result by Lurie, which proved, let's say, half of the cases. So basically, the inner case would be in our language. We pieced that together, and we managed to prove that indeed these 4 kinds of fibration do model functors into the infinity 2 category of infinity categories. So this is an unstraightening type of result. Some people maybe would call this a comprehension construction. We just follow Lurie's terminology for this. The proof is sort of using a trick where we apply some leverage on Lurie's proof, and we move everything to the world of Marx simplicial categories and then work there where dualities are simpler to deal with because they are sort of on the nose dualities. And I'll say that in a second. So given a Marx simplicial category, which is a category enriched over Marx simplicial sets, this thing can be thought of as being a model for an infinity 2 category because it is enriched over something that models infinity 1 categories, namely Marx simplicial sets. So we can work in that word, and which we know to be equivalent to our framework. And it is possible to define what an inner co-Cartesian fibration is there, and also outer, which is the, okay, it's sort of the next transition. So basically we require a sufficient supply of co-Cartesian lifts, which are defined again by the pullback, homotopy pullback at the level of Marx simplicial sets that constitute the Ohm spaces. And then we require the local action, so this means the map between the Ohms, to be a marked right fibration of Marx simplicial sets. If you don't know what a marked right fibration is, just think about a right fibration and just delete marked everywhere, basically. So given a Dwyer-Kahn fibration, there is this nice coherence theorem that we've proven that basically this is a fibration in this sense, if and only if the nerve construction gives you a fibration in the previous sense, the one that I've just described. So the nerve, which is an equivalence, I haven't described what the nerve is, but it's just a way of translating between the two words, in fact, creates these vibrations. So we use that to prove the thing I said before. Okay, so to define, we need a more powerful, in a sense, something that's able to, a more expressive, I would say, construction for the join, which comes in 2 forms, so the inner join and the outer join. And to get this, we make use of an unbiased construction of the great tensor product. So this means that the input is now n infinity bicategories, if you like, or just scale simplicial set, Marx scale simplicial sets, and we get something that is the tensor of of n of them, because this is not associative otherwise. So we need sort of an unbiased definition for this. And we make use of this to define a join construction. Some of you may be familiar. This is exactly the same you have for infinity categories, just with the great tensor product replaced by the Cartesian product. And these joins are needed because now we have 2 possible variances for 2 cells, and the ordinary join of simplicial sets is not going to be enough. But the outer join is equivalent to the sort of point set theoretic join that's the usual one for simplicial sets. These joins come with right adjoints as usual. So we have slices, and we have 4 kinds of slices. We have over the diagram, under the diagram, inner and outer. And these are the isomorphisms that define them. It's pretty easy to sort of, if you're used to these kind of things, it's basically just once you have the join, you need to check a couple of things, and then you get somehow the slices for free. as a corollary of the equivalence that I mentioned earlier between joints, we have that the ordinary slices are equivalent to the outer ones, but not the inner ones. I think I will skip this part here. This is just about representable fibrations. So which fibrations are those of the form projection from the slice onto the base? I want to skip that and go on to the sort of more important stuff. So, and we want to define what a limit and a co-limit is. We need a notion of a cone on a diagram. And this is achieved by taking a suitable joint with a point to the left or to the right of the indexing category, just like we do for just like we do in ordinary infinity category theory. So once we have that notion of a cone, then basically something is a limit if and only if when you restrict from the cone, from the slice over the cone to the slice over the diagram, you get an equivalence. So you don't lose any information somehow. It's universal in this sense. This is the exactly the same definition, provided you have the more enhanced notion. And once we have that, we were able to prove that indeed this definition gives you back the usual equivalence. In this case, this is an equivalence of infinity categories. So mapping into the tip of the cone is the same as giving a cone with this terminal shape into this tweaked Ohm functor. So this is the usual thing. And then inner and outer basically gives you a lax and off-lax transformation. So maybe the other way around. There's a little bit of a clash of terminology, and I don't remember which one is which. We can also do something a little better, and we can also consider weighted limits and co-limits. So this time we're given a weight, which is valued in the infinity 2 category of infinity categories. And we're interested in computing the limit of a diagram weighted, or the co-limit weighted by this, instead of just the terminal one. So instead of just conical ones. And this is done simply by taking the corresponding, let's say, Grothendieck construction. So the fibration corresponding to the weight, precomposing and calculating the limit of the precomposition. Just like for ordinary category theory, it's the same idea. You just have to prove that it works. And the nice thing is that you do get the natural equivalence that you would expect. So mapping into the tip of the cone, let's say into the limit, is now the same as giving not just a cone with a terminal shape, but now the shape is determined by W. So we can recover all the weighted limits and co-limits that one is interested in. And a nice, let's say, sanity check is that if you have a Marx-Simplicial model category, which is a model category which is enriched tensored and co-tensored over Marx-Simplicial sets as a model category. So you have this enriched Ohm, and then you have the double, the two variable adjunction. If you're in this sort of setting, then there is a classical notion of what it is, or what it means to calculate the weighted homotopy limit, which is basically just the thing you would expect. You just take this this tweaked Ohm, as I said, and then you have the natural transformations and so on. And such a model category can be viewed as an infinity 2 category. There's a nerve construction for that. And the two notions agree. So weighted homotopy limits and co-limits coincide with weighted inner limits and co-limits of the corresponding infinity bicategorical nerve. And the outer thing is achieved by applying a co, so by reversing two cells. And so this also tells us that this nerve is going to be complete and co-complete because we know that such model categories are. So this, for instance, tells you that cut infinity as an infinity 2 category is all weighted limits and co-limits, for instance. Okay, the final thing, I'll wrap up in a minute, is co-finality. So co-finality means that essentially you have a map that creates limits or co-limits, and you hope that it simplifies calculations. It is its calculations. So for this, we need to know what an inner-outer Cartesian equivalence is. This is basically a map that sees every fibration as an equivalence. Okay, or you can say it's an absolute equivalence in a suitable model category, and those would be the co-initial and co-final maps actually. And so based on this definition, we can define what it means for a map of marked scale simplicial set, so we are marking in both dimensions. We can say that this is inner or outer cofinal, and then we have co-initial. So again, 4 kinds. If it is inner outer Cartesian, equivalence over L, so over its codomain. And the co-finality theorem is, which is sort of the thing you would expect from such a notion, is that being co-initial, inner or outer, is the same as essentially the third thing is the thing I'm interested in, that precomposing by the map preserves and detects, you could say creates the limit and co-limit cones. So precomposing by that, you don't lose any information if you want to calculate limits and co-limits. And that's everything I wanted to say. Thanks.
Thank you very much, Eduardo. We have plenty of time for questions. There's one here in the audience.
Thank you very much for your talk. It was really interesting seeing all this build up to get to Infinity 2 categories. I was wondering whether, because it seemed to me that it was quite straightforward what the property that you wanted to prove would be, like based on, for instance, what Lurie did. And in that sense, would you expect something similar to be done for Infinity N category, meaning that with the same methods, would you get easily the corresponding results?
I mean, it's really not that straightforward to see already in dimension 2 what you need to be true. I mean, you have some inspiration that comes from ordinary 2 category theory, sometimes generalizing what happens for Infinity 1, but already in going to dimension 2, there's already some there's extra difficulty, especially in for instance, for fibrations, you know what you want them to be, but defining them on the whole categories, it requires some work. As far as Infinity N, there is some work that's been done. There's a lot of work that's been done in comparing models, not a lot of work in developing the category theory of these things for n greater than 2. So there's definitely some abstraction in doing that. It's definitely not straightforward if you have n equal 2, but n equal 2 is a nice sort of ground case to study. But I mean, already, yeah, I mean, there's some stuff that's been done, some constructions like the great tensor product is available there, joints and slices are available for some models. Recently also a model for Cartesian fibrations of Infinity N has been proposed. But yeah, I mean, it's a whole new thing to be done, yeah.
Okay, thank you very much.
Any other questions up there? Yes.
Hi, yeah, also thanks for your talk. It's a great talk. Are there any model structures around? So all these types of fibrations in various model structures, either globally or sliced?
Yes. So there's so for instance, Lurie has a model structure for the inner version of these fibrations, and we are working with sort of towards the end of having a model structure for these for the outer case, basically. I mean, also the inner in our language is a little different, so there is something to prove there. But yes, there is. So the thing is, once you have the right lifting properties, for instance, once you have the equivalence with the enriched case, let's say, having the model structure is just it's more or less a combinatorial exercise.
Will there be the fibrations in a global model structure or the fibrant objects in the slices?
Fibrant objects in the slices.
I see, okay. And is there a model structure on the marked simplicity enriched categories with these Dwyer-Current fibrations?
I mean, there is a model structure just to have there's like a Dwyer-Kahn model structure to have the Infinity 2 categories. About the other thing you asked, I'm not aware that there is. And I'd have to think about if there are some obstructions in having that, because marked simplicial categories are in some respect a bit weird because there's an extra rigidity. So some things are less, I'd say, straightforward to do. But there's definitely a model structure just for the ambient, let's say, Infinity 3 category or Infinity 2 categories there. That's definitely there.
Thanks.
Any other question? There's one online, I guess. No, let's go ahead.
Yes. Hi, Eduardo. It's beautiful stuff. You and your collaborators have written so many great papers. It's difficult for the rest of us to keep up. And so in particular, there's a few notions which I'm still not quite on top of. In this talk, you spoke about inner and outer weighted limits.
Mhm.
To what notions in ordinary two-category theory do these correspond?
The inner outer basically rules the lax and off-lax aspect of.
Okay, so these are weighted, I guess this is what you said at the beginning, these are weighted lax or ob-lax
Yes.
limits or
Yeah, yeah,
boundaries.
yeah.
Okay.
Yeah.
So I guess
Oh,
that,
well, actually, let me say that it's more than that. Like because of the marking, you have a whole hierarchy of laxity that you can consider. So if you mark everything, you recover the pseudo one, I guess you would say.
right.
And if you don't, if you have the minimal marking, you recover the lax ones. And then everything.
This is like those sigma limits that
yes,
some people have talked
exactly,
about, right?
Yes.
Yeah,
Mhm.
that's good. Yeah. Okay, great stuff.
Time for one more short question.
I think there's one online.
Yeah, please go ahead.
Thanks for your talk, Eduardo. That was very interesting. I also have a similar question to Alex's, in that I was a little bit confused about one of the things you said and how it kind of translated to the usual two categorical story, because it sounded like what you were saying was if you have a weight for a diagram, then you kind of perform the Grothendieck construction for that weight, and then you can take the usual conical limit when you restrict your diagram along the kind of projection from the Grothendieck construction. But isn't that not the case in two category theory? Like if you have you know, a cat enriched weight, then you can't just reduce that to a conical weight. So I was a little bit confused about that. Maybe I didn't understand what the reduced what the usual two categorical thing.
I mean, perhaps there are more qualified people to speak about ordinary stuff than myself. I didn't spend too much time thinking about the ordinary case, but I think with I think it is true. It's just that the thing is here, you have to keep in mind that, of course, I've hidden some details during the talk, but when you perform the Grothendieck construction, you get a marking on the domain of this fibration, and this marking is imposing some coherencies on the resulting composite diagram. And when you take the colimit of that, these coherencies are taken into consideration. In the ordinary case, I would say that, I mean, if you wanted to recover just, it depends what you want, really what you want to recover, because some of these notions are not quite well encoded. As Alexander said, sigma limits are the closest thing, I would say, in that case. So you would recover the appropriate notion with respect to the marking that you get on the fibration. So that's the thing you would recover.
Okay, thank you. I think we have to.
Right, so it's the markings that allow you to kind of keep track of that extra information, essentially.
Excuse me, we have to move to the next talk. It's time now. Let's thank Eduardo again.
Thanks.